Hello students, uh, this is your lecture number 7, and today we will be discussing about the process control block, and we will give a definition about the context switch time and one of the CPU scheduling algorithm, that is round robin CPU scheduling algorithm. So just to summarize, what we have discussed in our last session was all about the process control, process state diagram, and some of the CPU scheduling algorithm like FCFS, shortest of first, preemptive and non-preemptive version, and the priority scheduling algorithm. Those were the CPU scheduling algorithm that we have discussed in our last class. So today, in addition to it, through this lecture, we'll be discussing PCB context switch time and round robin scheduling algorithm. So, as you all know from our previous session, that a process is a program under execution. The meaning is that whenever a process is being executed by the CPU, right? At that time, we say that the process is in execution, or program becomes a process. Whenever, okay, during the execution of any of the process, whenever the process demand for some IO activity, maybe the process want to use user input, or the process want to use uh, a printer, okay, any of the IO devices it want to use it, okay, then in that scenario what will happen is that the process will be either moved to IO in a waiting queue, right? So in a waiting queue, waiting for the IO devices to get it free so that it can use it, or it may happen that the current executing process may get preempted, like that way we are discussing the SJF preemptive. So in that case, again, the process will be shifted from the running state to the ready state. So in either case, if the process is shifted from running state to ready state, or running state to waiting state, in either case, whenever there is a transfer of process from one state to another state, right, from one state to another state, the operating system will save the state of various information about the process. Okay, so such all the information related to process will be stored in a particular part of the memory in some format known as a process control block. So I repeat, what is a PCB? PCB is a process control block which stores the informations, which the operating system store the information about the process. So what are the various different kind of information that operating system stores about the process? Okay, so you can see over here in this slide, there are lots of information about the process that operating system maintain it in the process control block. So it is not only necessary that whenever the process shifted from running state to ready state, or running state to waiting, not only for that, all the from new state to ready state, that is step also, that in that way, in that stage also, the operating system maintains the information about the process. So these are the list of information that operating system stores about any of the process, right? Any of the process in a particular data structure called a process control block. Okay, so process control block stores all the information about the process. So what are those informations? Process state, okay, like process may be in a ready state, running state, any of one of these state. So it stores that information. Next is the unique identifier, PID. So you can extract the ID of the any process using the get PID, or get PPID, etc., etc. There are a lot of system call which you can use it in the program to identify the process ID of any of the process. Next is the program counter. Now program counter is a kind of a pointer which points to the current instruction being executed, or which points to the address of current instruction being executed. Say for example, there are 5 lines of code in a program or a process. I repeat, suppose there are 5 lines of code in a program or a process. Now suppose CPU is executing third instruction. So the program counter will point to that address of third instruction. So that is the meaning of the program counter. Next is the CPU register. There are so many registers that is available in the with the computer systems general purpose register. So what are the various different kind of registers like accumulator, um, cache memory, etc. All those information registers information will be stored in the will information such information will be stored in these register informations. And scheduling algorithm, right? So we have discussed various kind of scheduling algorithms so far: FCFS, SJF, priority, and today we'll discuss round robin. So the process is being used by is uses the process, the current running process, the information about the process that operating system wants to keep record of it, that process, which scheduling algorithm is being used on that process, whether it is FCFS or whether it is SJF, etc. So those information will be stored in the CPU scheduling information. Okay, so next is the memory management. It stores the in this category, the operating system stores information regarding the memory management, right? What is the amount of memory, all right? And type of memory, so stack, heap, etc. All this information will be stored. Next is the accounting informations, so who are the users, etc. Okay, and next is the IO status. So what are the list of IO devices that has been used by the currently used by this process, or the going to use in the by this process. Like IO devices could be like in keyboard, mouse, printer, etc. So these are the list of information that operating system maintains for each and every process in a particular specific data structure known as a process control block. So this is all about the process control block. Now as you are aware that whenever a process state changes from one state to another state, okay, so operating system will maintain these informations, this list of informations in the process control block, right? So with this we will try to understand when the process changes its state, what will happen and how things will happen, right? Suppose there are two processes, the P0 and P1. Now currently, say for example, P0 is executing. So currently the P0 process is executing. Okay. Now suppose whenever the process P0 is executing, it is assumed that P0 is in a running state. Okay. Now suppose due to some reason the execution of P0 has been interrupted and has to be sent from running state to ready state, right? Due to preemption. Okay, so at that time what will happen is that whenever okay, P0 has to be suspended, an interrupt will be generated that will be sensed by the operating system. Now based on the interrupt that operating system has sensed, maybe through system call or anything else, okay, so what will happen is that operating system will save the current state of the process P0. Okay, so whatever is the current state, out of say for example 100%, 50% of task has been completed. Okay, and scheduling informations state, okay, it may happen that P0 currently is in a waiting state or running state, a ready state. So those all those information will be stored in the PCB. Okay, so so it will try to operating system will try to save the state of the process P0 in a PCB uniquely identified by subscript 0, right? So then after that what will happen is that from here, okay, once it is saved, okay, during the saving of process P0, during the saving of state of process P0, the computer will not do any task, right? The computer will not do any task. So till the time, okay, nobody is executing things, so that's why it's written over here as ideal. Now now after completing the saving state of process P0, suppose P1 is ready in the ready queue. Now P1 information will be loaded, right? P1 information will be loaded and CPU is assigned to it. So when CPU is assigned to it, it starts executing. Okay, so it start executing. Now that is also generate, that is also signaled with the help of the interrupt of system call. Now P1 will start executing. P0 has now sit in ideal because it has went to the some other state, maybe a non-executing state. Now P1 is executing. Now it might happen also that P1 may also get interruption for execution. So when it is interrupted, okay, p when interrupted, when p1 is interrupted for execution, again system call is generated or interrupt is generated. Again, operating system will save the state of process p1, okay, and till the time until until and unless it loads the um, saved information of process P0. Again P0 will start executing. So this is how, suppose in a scenario of computer system where only two processes are the P0 and P1, this is how switching of one process will takes place from one process to another process, which leads to an intermediate step like saving the state of old process and loading the new process, those information. Now there is something called context switch time. Okay, there is something called context switch time, that is the time elapsed between saving of one state and loading of another state. That time is known as a context switch time. So context switch time is the time overhead or the wastage of time. In a computer system we cannot have too much of context switch time, because we want to utilize the CPU time efficiently. So context switch time is a time elapsed between saving of one state and restoring of another state of the two different process. So those time is known as, or that time is known as a context switch time. So in a computer system it is always good to have a minimum context switch time. So context switch time is a time elapsed between, context switch time is a time elapsed between saving of one state between and reloading of another process, right? So from here to here, the computer system will sit idle, and this time is known as a context switch time, right? So this is all about the context switch time. Now we'll look into the one of the scheduling algorithm. So just to give you a brief about previous scheduling algorithm that we have discussed. So first of all, scheduling algorithm is responsible. CPU scheduling algorithm is a kind of a, is a short-term scheduling algorithm which transfer a job from a ready state to running state, right? So now there are various kind of CPU scheduling algorithm: FCFS, SJF, preemptive, non-preemptive, and a priority, and the next one is the round robin. Now out of this list of the various CPU scheduling algorithm, some of them are preemptive and some of them are non-preemptive. In case of preemptive, the execution of currently executing process may get interrupted, right? However, in case of non-preemptive, once the CPU is given to a particular process, the process will not release the CPU or resource voluntarily. Okay, voluntarily. So it will not release the resource until it gets completely executed. Okay, this is all about the various CPU scheduling algorithm. Now we look into the round robin. Round robin is very kind of a fair CPU scheduling algorithm, which gives equal chance to all the process for executing its task. Unlike in our previous CPU scheduling algorithm like priority or SAF, where we have seen that the process with the large burst time or the lowest priority will never ever get chance to execute, because the priority is less or the burst time is very high, and every time, in every clock pulse there are some high priority task or the process that is always coming up, and the old process, okay, who is having the low priority or the large burst time will never ever get chance to execute, leading to a problem of aging, right? So we don't want such kind of discrimination among the process. So it's a round robin who doesn't discriminate on the process based on its priority or based on the size of the burst time. So CPU scheduling algorithm is a very very general algorithm which uses the concept of time quantum. Now this algorithm is associated with a particular data structure called a time quantum. Time quantum is kind of a timer. So every scheduling algorithm, okay, that is round robin scheduling algorithm, is associated with some time quantum. That time is a time given to each and every process equally throughout, okay, um, for executing their task. Now, it is also sometimes it is also called to be a FCFS. We will come to know at what situation round robin can also be considered to be FCFS scheduling algorithm. So we'll discuss this later on. So as of now, we'll see very very simple scenario. Okay, say for example there is a three process J1, J2, and J3 with burst time 24, 3, and 3. I am not considering arrival time. All these three processes have been arrived at the same time at time t equal to 0. Okay, so in this order, so J1 in this order they have arrived, although they have arrived at the system at the same time. So the time quantum, as I've already told you, and the time quantum given to this snapshot of the system is 4. So meaning time quantum 4 meaning is that 4 milliseconds, say for example the unit is millisecond, 4 millisecond is given to J1. Okay, so whether it completes or not, okay, whether J1 completes or not, after 4 millisecond the CPU will be given to J2. Okay, again J2 will execute, will be J2 will be given for 4 units of quantum time. Okay, but here you can see that J2 requires only 3. So out of this 4, J2 is using only 3, right? So it's okay, fine. Once J2 complete its execution, again CPU will be given to J3. Okay, and same is the scenario, and it will repeat, okay, again and again, just like a circular cube. Okay, so you can have a look on the Gantt chart. So initially P1 is given for 4 units of time. Okay, then after that P2 come. Okay, because P2 was in the next sequence. You can consider P1 is equals to J1, P2 is equals to J2, and P3 is equals to J3. Okay, similarly, after completing P3, again P1 will get chance. Now, since both of them have already completed, okay, CPU will be given to P1, P1 again until unless it completes task. So now, whenever CPU will switch from P1 to P2, I repeat, whenever the CPU will switch or CPU will be snatched from P1 and will be given to P2, there is some context switch time that I have not shown out here. So I am assuming in all the scheduling algorithm, especially preemptive, I am assuming that context switch time is 0. If you don't consider context switch time, okay, if you consider context switch time, your calculation will become practically difficult. However, in practical system, context switch time is always there. Okay, so we will see some more example about the round robin scheduling algorithm, okay, so that it becomes easier for you to understand. Say for example, there are four processes P1, P2, P3, and P4 with burst time 53, 17, 68, and 24, and they have arrived at the system at the same time in this order P1, P2, P3, P4. So very obvious that P1 will be given first chance to execute P2. Sorry, P1 will be given first chance for using CPU, and after time quantum is over, P2 will be given the next chance. Again, P2 will be given with some time constant, quantum, and once time quantum is over, P3 will be given the CPU. Again, after P3 timer is over, P4 will be given. Okay, and again CPU will go back to P1, provided if there is some leftover burst time with P1. Okay, if any one of the process is complete, it will be exiting the system, right? So in this example, I have considered the time quantum to be a 20. So 20 milliseconds will be given to each and every process for completing its task. Once the time quantum is over, the process is preempted and CPU will be given to next process in sequence, right? Okay, so first of all, P1 is given for 20 units of time. So out of 53 burst time, 20 is completed. 20 units of P1 is complete. So remaining is 33. So 0 to 20, P1 will get CPU and will execute 20 units of 53, so remaining is 33. Okay. Next, at 20, P2 is given, okay, because the quantum assigned to P1 is now over, or timer is over. Okay, so P2 will execute for 20 units. Okay, so out of 20 units, only 17 units were usable to P2, so remaining is 0. So 20 plus 17 is 37, right? Fine. Next is P3 in sequence. So P3 will get chance. P2 have completed and exited the system. So P2 is not at all required next time. So now the CPU is with P3, and the burst time for P3 is 68. So 20 unit is assigned. 20 millisecond is assigned for P3 for executing its task. So out of 68, 20 units is consumed or used or executed, so remaining is 48. So P3 37 plus 20 57. Okay, now at 57 the timer assigned to P3 will get over, and CPU will be given to P4 by preempting P3. So P4 will be given a chance for executing 20 units. So out of 24, 20 units will be consumed, or will be executed, so remaining 4 is left over for P4. Okay, now after this, after completing, after the timer is over, or after the quantum time is over for P4, CPU will be again given back to P1. So it's a kind of a circular queue. Whenever you are implementing round robin, you have to consider it as a like a circular queue, right? So P1 is given a chance. P1 is given a chance. So out of 33, okay, 20 will be executed, okay, and remaining 13 will be left over for P1. Again after that, P2, it's not at all required because P2 has already completed it and has exited the system. So P2 is not at all in the scene right now. After P2, P3. Okay, so 48, out of 48, 20 is utilized, so 28 is remaining, so leading to 97 plus 20 is 117. Okay, again, so P2 I have marked P2 I have marked green because it has completed its execution. Okay, so P3 now after executing 20 units, remaining is 28, it has not yet completed. Now coming to the point P4. Okay, P4, it will execute for out of 20 units assigned to it, 20 millisecond assigned to P4, out of only 4 it has utilized. Okay, so as and when it completes, P4 completes, CPU will be immediately released. Now in this case, once the process complete, it will release voluntarily. In case of the other case, earlier case, what we were doing, process were preempting. Okay, forcefully stopping or snatching this CPU from the process. But once P4 completed, it has released the CPU voluntarily. Once it releases the CPU voluntarily, the operating system will manage it to give it to next process in the sequence. So P4 will complete it. So that's why uh, P4 is marked as a green color. Now after completing it, so P3 has completed 117 plus 4 units, so that's why 121. Now again P1 will execute for 20 units, so P1 will also get completed, so that's why I have marked as a green color. Then after that, P2 was not in the scene. Okay, P3, okay, P3 will get executed, okay, and then will get completed, fine, and P4 had already completed. Now if I follow this uh, Gantt chart, or if I see this Gantt chart properly, P3, say for example, let us focus only on P1. Okay, here in this Gantt chart, P1 has not waited in this block. However, P1 has waited in this block. So how much amount of time P1 has waited here? 77 minus 20. This 77 minus 20, whatever is the answer, that much amount of time P1 has waited. Plus, right? P1 has waited here also. P1 has waited here also, from here to here, 97 to 121. So 121 plus minus 121 minus 97, whatever is the answer, plus the older waiting time, is the total amount of waiting time waited by the P1, right? Waited by the P1. So for example, let us check for the P4. P4 have waited for twice. At here also it has waited, and here also it has waited. At 57 also it has waited, at 117 also it has waited. So I'm assuming that all the processes have arrived at time t equals to 0. So P4 have waited for 57 units of time at here. Okay, plus here also it has waited. How to calculate this? 117 minus 77. So whatever is the answer plus 57 is the total amount of waiting time for process P0. So after calculating the waiting time of each and every process, we can calculate the average waiting time and coming out here as 73. Now if you change the quantum value from 20 to some, say for example 30. Okay, if you change the quantum value from 20 to 30, so average waiting time now is 68. So earlier it was 73. So now selection of the time quantum also matters a lot in case of improving the efficiency of the round robin algorithm. So the selection of a quantum plays a vital role in improving the performance of the scheduling algorithm. So we cannot keep the quantum time very large if we, okay, unfortunately if we try to initialize or use the time quantum very large time quantum, then it is equivalent to FCFS. However, if we choose very small time quantum, then what will happen is that there will be lot of, practically there will be lot of context switch time, because here we are not calculating the context switch time, but in practical scenario there will be a context switch time, right? So there, if we keep very small time quantum, there will be very too much of uh, context too much of context switch will be occurring, and which is leading, or which will be wasting the CPU time or the computer system time, which is really an unwanted scene, right? So this is all about the theory of the round robin. You can have a look. PPT is already uploaded, right? So this is all about the round robin and the PCB and the context switch time. So thank you so much. If you have any questions, please do upload the um, um, doubts, or the you can have a discussion, okay, in our discussion session. Thank you so much.